This tutorial is an introduction to radioactivity. I'm going to go through the following. So the structure of an atom, the types and properties of radioactivity, the decay equations, and activity and half-life. So to understand radioactivity, the first thing we have to understand is the structure of the atom. So our atom, as you can see, is made up of a nucleus. Within the nucleus, you've got protons. I've shown these as coloured in black here, and neutrons. Protons have a positive charge, a relative charge of +1, and a relative mass of 1. The neutrons have no charge and a relative mass of 1, about the same mass as the protons. They are in the nucleus. Orbiting around the nucleus, you have electrons. The electrons are very small, usually considered to have negligible mass, although sometimes you might see that they are have a relative mass of 1 over 2,000, sometimes 1 over 1814, the mass of a proton or a neutron. In this example here, I have 4 black blobs, which I've depicted as protons, 5 white blobs, which are the neutrons, and 4 electrons orbiting around the outside. Now, knowing these numbers, we can put together a symbol for this particular atom. The protons and neutrons, they have mass, so together the total number of those tells us the mass number here. So 4 protons, 5 neutrons, we've got a mass number of 9. The bottom number here, the atomic number, tells us which atom it is. Which atom it is depends on how many protons it has. In this case, we have 4 protons, therefore the element must be beryllium here. For a general form of your atomic symbol, we depict the symbol as an X, meaning it could be any element symbol, A as the mass number at the top, and Z as the atomic or proton number. If you look on your periodic table, this will give you your symbol with the correct number of protons here for your atomic number. Down here, I've put in the table what we talked about, the relative mass and relative charge of each of those particles. Now, why that's important to radioactivity? If we get a very large atom, usually a very large atom, it doesn't have to be, sometimes that nucleus can be unstable. And if it is unstable, it tries to do something about it. It will release particles and release energy in order to gain stability. Now, there are a few ways it can do this. It can undergo alpha decay, it can undergo beta decay, or it can lose some energy as gamma rays. Notice in this diagram here, I've not drawn any electrons. If something is radioactive, it is the nucleus that's unstable, and the electrons do not play a part in this process. To undergo alpha decay, what this means is from the nucleus, we have an alpha particle that is emitted. Now, an alpha particle is made up of 2 protons. So you can see in a similar way to the other symbols, we've got a 2 down there representing 2 protons, and 2 neutrons. So 2 protons, 2 neutrons. It has an overall mass of 4. We usually give it the alpha symbol, the Greek lowercase letter a, but sometimes you will see it represented like this, helium. Now, this is a helium nucleus, not the electrons, because helium has 2 protons, and when it's got the 4 there as well, it means that it has 2 neutrons as well. 2 plus 2 is 4. To undergo beta decay, this one is slightly more difficult to explain, because an electron, something of 0 mass but a charge of -1, is emitted from the nucleus. Now, when we looked at our diagram of the atom before, there are no electrons in the nucleus, so something more complex is happening here. And what's going on is that one of the neutrons from the nucleus, the unstable nucleus, breaks up and it forms 1 proton and 1 electron, and the electron is ejected from the nucleus. So the effect of this is that it will change the atomic number, it will increase it by 1, although the mass number will stay the same. For your helium nucleus or your alpha particle, you're losing 2 protons, 2 neutrons, so your mass number will go down by 4 and your atomic number will go down by 2. The third type of radiation is gamma waves, which are a form of electromagnetic radiation. Now, these are waves, they are not particles. They have zero mass, zero charge. So gamma radiation changes nothing at all about the nucleus except reducing the energy. So this normally happens alongside an alpha or a beta decay. Now, your alpha particle, 2 protons, 2 neutrons, because it's got 2 protons, it's got a relative charge of +2. A relative mass of 4, and it travels very, very slowly, well, relatively slowly, 1/10 of the speed of light. Your beta particles, charge of -1 because they're like an electron, and they're reasonably fast, 9/10 of the speed of light, but your gamma radiation, zero mass, zero charge, will travel at the speed of light. It's an electromagnetic wave, just like a light wave. So your alpha and betas and gammas, what more do we need to know about those? Well, your alpha particles, which have got this +2 charge, they are very ionizing. By ionizing, we mean that they can remove electrons or add electrons in some cases to atoms. So because these are a +2, they will probably rip off electrons off other species there, and therefore they then will become a neutral helium and then be completely inert. They're not a danger anymore. So they only travel a few centimetres in air because they will interact with the air particles. They're stopped by paper because they will interact with the paper, stopped by human skin. So very, very low penetration, but do cause a lot of damage. They could potentially cause a lot of damage because of how ionizing they are. Your beta particles, as I've said, this is when a neutron turns into a proton. They still have a charge, they're -1, so they are still ionizing. In the scheme of things, we say that they're moderately ionizing, and so they travel moderately far as well. So their charge is less, they get to travel a bit further before they make some kind of interaction. They're stopped by a sheet of aluminium or tens of centimetres of air. Your gamma rays are high energy waves, but they are uncharged. So out of the 3, these are the lowest in terms of their ionizing ability. However, they do still cause some damage. They can travel meters in air, and they will pass through many objects. So your paper, the skin, the aluminium sheet that the beta was stopped by, it will pass through all of those. In order to block a gamma ray, you have to stop it by a sheet of lead, or a thick sheet of lead, or meters of concrete. So they penetrate to a much greater effect than the previous 2. However, they are uncharged, so they are not as strongly ionizing. Moving on to decay equations now. If we take a look at the examples here, first example is an alpha decay. So we have a uranium atom here, 92 protons, that's what makes uranium radioactive. That's what makes uranium uranium, the fact that it has 92 protons. Mass number of 238, so the sum of the protons and the neutrons there. Unstable nucleus, it will decay using an alpha particle, 4-2. Now, what happens to the nucleus? Well, it loses 2 protons and 2 neutrons. So our atomic number, or proton number, will go down by 2. It's lost 2 protons. So where it was at 92, it now goes to 90. What element is it? Well, you'd have to look at your periodic table here if you didn't know it. So 90 is the element with the thorium is the element with 90 protons, so we would get that symbol looking at the periodic table. The mass number, you need to look at the decay equation here. So 238, it's lost 4 particles with mass, 2 protons, 2 neutrons, therefore reduce that by 4, 234. So have a quick look at this one. We've got polonium here, that's 94 is the atomic number, and this isotope has got a mass number of 238. It's going to lose an alpha particle. Uranium is going to be the product. So have a few seconds and think what those numbers will be. If you said 92 down here, that would be correct for the atomic number, just like our uranium here. And the mass number here will be 234. Notice that it's different from this one because we can have different isotopes of the same element. So isotopes are something that have the same number of protons but a different number of neutrons. Not all isotopes are radioactive, only certain ones. So again, I'll repeat, this bottom number should be 92 and the top number 234 as the mass number. We'll now look at beta in terms of a decay equation. And this is carbon-14. In naturally occurring carbon, there's a very, very low percentage of carbon-14, which is radioactive. When it decays, it releases a beta particle from the nucleus, as I said before, by a neutron breaking down, forming a proton and an electron. The electron is ejected here. So since our proton has been formed from a neutron, our atomic number will increase by 1. The mass number will stay the same because a neutron, it starts off as a neutron, that has 1, it turns into a proton, that also has a mass of 1. Also check that everything is balanced on each side of the arrow. So here, a total mass of 14, total atomic charge of 6, 14 and 0, 14, that's the same on both sides. And then in terms of our atomic number or charge in the case of the electron, 7 minus 1 makes 6. So that's all balanced there. Have a go at this one here. So this time I've given you less information. You've got a lithium isotope, atomic number 3, mass number 8. It undergoes beta decay. You might need a periodic table if you're not sure what it would be, but have a quick think about that. So for this element here, we need to have an atomic number which is 1 greater than 3. So this must have an atomic number of 4. So little 4 at the bottom. 4 minus 1 makes 3. Now at that point, look at your periodic table, find which element has the atomic number of 4. It's beryllium. So the symbol here is a capital B, lowercase e, Be for beryllium. The mass number is unchanged. So we should have an 8 at the top here, a 4 at the bottom there, and the symbol Be for beryllium. We don't tend to write decay equations for gamma radiation because the element is unchanged. This will happen alongside alpha and beta, and it's just energy that's being lost. The last thing I'm going to talk to you about is activity and half-life. And there are a few facts and a few definitions that you'll need to know for this section. So when we're talking about activity here, we're talking about the decay from the nucleus. So radioactivity is a random process. We can't get a sample of radioactive atoms and say this nucleus is going to decay next. We can't tell which one will go next. However, we can get some information about the rate at which the sample will decay, and this is known as the half-life. So the half-life is defined as the time it takes for the number of nuclei in your sample to decay by 1/2. Now, how do you measure the radioactivity? You measure that using a piece of equipment called a Geiger-Müller tube. That will detect the radiation or the charges presented from this, and a counter, which sometimes they click, sometimes it's like a needle that will ping one way or another, so it will detect there. The half-life, we can use that to then find the rate at which it decays. That's known as its activity, the rate. The units that we use to measure this are known as the becquerel, given the symbol a capital B, lowercase q, and 1 becquerel is 1 decay per second. So there are 2 ways of defining half-life. One is in terms of the number of nuclei, so it's the time it takes for half the number of nuclei in a radioactive sample to decay by 1/2. Or you can express this in terms of the activity. So if you've got a certain count rate per second or count rate per minute, whatever is relevant to your sample, it's the time it takes for that count rate to drop by 1/2. So when you see this on a graph, it's possible that you can get 2 possible axes on your graph. One talking about number of nuclei or percentage of your nuclei remaining, or another one talking about activity. I'll show you that in a moment. So let's look at this example here. The activity of a radioisotope is 640 CPMs, that's counts per minute. 2 hours later, it's fallen to 80 counts per minute. From that information, we're able to work out the half-life. Now, this is the way I would suggest to you to do it. I find this the easiest way. Start with what you've got initially. So here's 640. Draw an arrow, that's representing your half-life here. So we've got 1 half-life passing. So if it started at 640, after 1 half-life, that will have dropped by 1/2 to 320. Now let's do it again because we're not at our target of 80 here. So we're going to have another half-life pass. That will take us to 160, and 1 more half-life takes us to 80. How many half-lives have there been? 1, 2, 3. Count the arrows there. So you can see that we have 3 half-lives, and that is taken a total time of 2 hours. So what must be the half-life of this sample? Well, in 120 minutes, 3 half-lives have passed. So for 1 half-life, that must be 40 minutes. Let's look at another example, a numerical example like this. Now this one is a slightly more tricky one because of the wording in the question. So if we have the initial activity of a sample at 640 becquerels. Now the question here is to calculate the percentage reduction after 2 half-lives. So first things first, let's go about as we did before. Start with 640, 1 half-life, 320, 2 half-lives down to 160. Now the reduction, this is the key here in the question, the reduction is the difference between your start point and your end point. So 640 minus 160, we've had that count rate reduced by 480 becquerels. So our percentage reduction is how much we've been reduced by, 480, divided by your total, 640, multiplied by 100 because it's a percentage, so it's been reduced by 75%. Now the graphs that you can get for half-life, like so. As I said, on your y-axis, you need to just be careful that you look here. This one is written in activity, so this will be in becquerels, and so you'll have some sort of number here. It might be that it's percentage of the nuclei remaining, in which case it will normally start at 100% and then fall down accordingly. So if you have a graph like this, it's possible to calculate the half-life. What you would do, you can start anywhere really on the graph. It's normally easiest to start where you've got 100%, in this case 80 becquerels here. Look down your axis and find where that value has dropped to 1/2. Now if you're ever asked to show how you're using the graph, you must draw in your lines on your graph. So get a ruler, draw a horizontal line from your halfway point, then when it touches the curve, turn your ruler around and draw it down. Now that first section here between 0 and where your vertical line is 1 half-life. If you needed to verify this with a second half-life, again, you can start anywhere, but normally it's easiest to say, well, if I've got 40 here, let's that drop down to 20 and repeat the process. The second half-life, you measure it from the point that you've ended here and to the beginning point here, not from the 0. So at this point, this was the time at 40, and we're measuring the new one at a count rate of 20. So you look at that point here. If you did it a third time again, so 20 divided by 210, read across down, and again, your half-life is from the previous one to the end point here. In this case, you can see we've got 4 to 8, so that's another 4, 8 to 12, another 4 here. So whatever the unit this is, be it seconds or minutes, we've got the time for our half-life will be 4. So in summary, what you should have been able to got some information about in this video: structure of the atom, the types and the properties of radioactivity, decay equations, and then a little bit on the activity and half-life.